very good. So thank you very much for the opportunity to present my work. And today I'll be mainly talking about this first work here that I did in collaboration with Michele Ciccoli, Veronica Guidetti, and my supervisor, Alexander Westphal. But I will be using also some results taken from this other work that I did with Federico Carta, Alessandro Menino, and Alexander Westphal. So let me start by showing you the main result of this work. So what you're seeing here is our prediction of string axions behaving as possible fuzzy dark matter candidates. And the plan of my talk will be actually to go through all these different bands that are the results of this work, to comment them, to comment how we got them from a type 2B Calabi-yau compactification. And the main point of my talk will be to show you that if, as you can see, if we will ever be able to detect the fuzzy dark matter, then this can also be a possible detection of the string axiverse, because we will provide many candidates from string theory. And this will entail also some hints on the compactification, on the features, and also on possibly on the weak gravity conjecture bound. So let's start by explaining what I mean with fuzzy dark matter. So famously, the cold dark matter scenario has some problems. So for example, the cold dark matter has the problems of the so-called cascore problem, and also the missing satellite and too big to fail problems. All these problems comes from when we study cold dark matter halos on small scale sizes, so namely on the scale of galaxies. And they all comes from the simulations, the cosmological simulations of cold dark matter halos. So for example, here you see a simulation of the cold dark matter halo. And as you can see, cold dark matter tends to form all these different structures. However, these simulations here are quite different from what we actually see from the observation of galaxies. For example, a halo of cold dark matter tend to have a cusped density profile at the center of galaxies, but this is not seen by observations. And also, as you can see here, the halo of cold dark matter tend to form these low mass halo structures all around the galaxy, but actually it tends to form too many of these low mass halos, and we don't see them as much. So one of the proposals to solve all these problems goes back to actually 20 years, and is the so-called fuzzy dark matter. With fuzzy dark matter, that a simulation of a halo is this one here, is a type of dark matter which is made of ultralight particles, and these particles should be so massive, so they should have such a small mass that basically their nature is almost wave-like, and therefore they are able with this property to smooth away all these structures that a cold dark matter scenario form, and therefore also to solve all these problems here.
Can I interrupt you 1 second? Sorry.
Yeah, sure.
Excuse me, are we sure these are problems?
Well, okay, there are many
like baryons in the simulation, if we could do it the right way. I'm just curious about your opinion. I'm not trying to undermine what you're saying.
Okay, so there are many ways to actually solve this problem and not to see that as a problem. I do agree. So for example, there is this how to solve this missing satellite. That can be also that all these low mass halos, we cannot see them, for example. This is one way to easily solve this problem, and therefore it's not really a problem. But if you see them as problems of the proper cold dark matter scenario, then it makes sense to look for other candidates for dark matter, no? Yes.
Absolutely. Thank you.
Thanks. Okay, so as I was saying, then it was proposed that such ultralight particles could in fact be axions, ultralight axions specifically. And it was computed that in order to solve all these possible problems of the cold dark matter scenario, then such an ultralight axion should have this range of mass and decay constant. Indeed, this was pointed out as a possible sign of the string axiverse because of this very high value of the decay constant, and also a possible clash with the gravity conjecture, because in fact, when one's compute the value of the instant on action able to provide such a mass, and then if we multiply it with this decay constant, then this bound is saturated if and also a bit slightly violated. However, we will phrase this in another way, in the sense that the particle which is responsible for the fuzzy dark matter is actually highly sensitive to the extremality bound entering the weak gravity conjecture. This is very interesting because this means that studying something that we could actually see via experiments could also give us some hints about the underlying theory of quantum gravity. And this is what got us really interested in this business. So to set the notation, this is my four-dimensional Lagrangian of my axion and the typical mass scaling of an axion-like particle in string theory. But the most important thing is this formula here, which is the main formula that I will use from now on, and is the formula that we use to compute the fuzzy dark matter abundance. And this is computed, of course, before the inflationary epoch, because the decay constant is higher than the Hubble scale at the inflationary epoch. And so the main character of my talk will be, as you already know, the mass of my axion, the decay constant, and also, importantly, the instanton action, which provides the axion with a mass. So, as I said, we are interested in particles that can basically saturate the weak gravity conjecture bound. And so we are interested in axions that has the biggest possible f times f value. So we work in the type 2B axiverse. So we take type 2B, we compactify it on a Calabi-yau threefold with O3 or O7 oriented fold planes. And this is my axiverse. And all these values that you see in this column actually are computed for the easiest geometries that you can think of. So, for example, a very small number of H11. So we take H11 equal to 2 or maximum 3, or maximum, sorry, H11 equal to 1 or maximum 2. And we see that actually C0 and B2 cannot be viable candidates because notoriously they are stabilized at higher energies and therefore they will have high masses. However, all these other candidates are actually viable candidates. So this is the axion coming from the harmonic C2 form. And then we also have the axions coming from the C2. And we will consider when we have only one of these axions and also when we have two axions. And also this particular type of axionic modes, which are called thraxions, and I will explain you later on what I mean with this. So let me start with the easiest example, that is the C4 axion. The C4 axion, to be so light, should be stabilized in the large volume scenario. And in particular, we should take the axion, which is the partner of the modulus corresponding to the volume of my Calabi-yau, and I parameterize my Calabi-yau with the Swiss form. And these are the results that we get. So we are making all the microscopical parameters of the theory. We allow them to vary in a very huge range. And here I'm plotting the abundance of fuzzy dark matter with respect to the mass of my particle. And as you can see, we get quite sharp prediction, both for the mass, but in particular for the decay constant. And this is quite surprising because really all the free parameters are varying a lot. And also then we consider the fiber Calabi-yau again in the large volume scenario. And we have this time two different axions here, the one corresponding to the base of the Calabi-yau and the one corresponding to the fiber. And again, we get the right mass scaling for the more or less for a possible fuzzy dark matter candidate. And here I'm showing a regime where the masses of these two axions are actually democratically distributed. However, if I slightly detune this parameter, we will go back to the Swiss cheese case that I showed you before. So where one axion is basically dominating all the dark matter and the other one is staying basically massless. So this is why we are also taking very easy geometries, because anyway, in the large volume scenario, they tend, even if I take more non-trivial geometries, they will anyway tend in the large volume scenario to these easiest geometries here. Okay, so these are the particular prediction, but then we can start to build the first plot that I showed you in the first slide. And here I'm plotting the mass of my fuzzy dark matter particle, and here the total abundance of matter inside the universe. And therefore, this means that since that we know that the dark matter should be the 25% of the whole abundance, almost of the whole abundance of matter of content in the universe, then this means that this point here corresponds to 100% of dark matter composed by fuzzy dark matter. And as you can see, the C4 axion is actually a very good candidate. And so we found our first candidate. So now let me give you some details about the compactification, which is able to provide this strip. So scenario, otherwise the axion will never be that light. And also there is a preference for a small number of branes wrapping the cycle. And very interestingly, there is a preference also for small values of the total Calabi-yau volume. And this was shown also recently in this paper, for example, that this is statistically favored in the landscape. Also, as I stressed before, these predictions are independent on the microscopical parameters of the theory. So actually, the C4 is a really, really interesting candidate. But then we wanted to really look at every possible axion. So we also checked what happens with the C2 axion. So the way to give a mass to the C2 axion could be via 81 brane instanton, so correction to the K potential. And they saturate in this way the weak gravity bound. But also we can consider a bounded state of 83, 81 instantons. And this is the value that we find for the product S times F. And this is quite interesting because this is enhanced by the volume of the Calabi-yau. However, let me say that this is not a violation, a proper violation of the weak gravity conjecture, because probably we should not apply the weak gravity conjecture to this guy here, because we are this is an effective effect that you can have when you couple an 83, 81 brane instant. But anyway, if you have an 83, you will always have also a C4 axion in the game, which is satisfying the weak gravity conjecture. So we are not by no means violating the weak gravity conjecture, at least in the mild form. And these are the results for the C2 axion. So this is the C4 axion strip that I showed you before, but then these are my new strip. So it's interesting, the 81 brane instanton case, because in this way we could have also a candidate, a possible candidate in KKLT. And it's the only one that we will have throughout this talk. However, when we tried to plot this guy, it turned out that it was too light to be actually a fuzzy dark matter candidate, because it is so light that it will never form the dark matter halo that we want. And so we had to discard it, but we wanted to plot it anyway because it was the only possible ultralight axion from KKLT. But then we see that the C2 axion in LVS can have both this strip coming from 81 brane instanton and also this strip in light blue here coming from the bound state of 83, 81 instanton. And what is particular at this stage of this point is that each axion has his own parameter space, and they are all they all come in distinct strip. So that's really interesting, because if by chance someone will detect something in this parameter region, then we will know exactly which is the good candidate to provide such a particle without uncertainties. So some comments about the compactification. As I told you, there is also a possible candidate for KKLT, but then we realized that it is actually slightly too light to be a good candidate. And also this entails taking very small values for W0, while in LVS, these times we have preferences for slightly bigger values. While in 83, 81 bound state, again, it works only for LVS, and we have, again, volume scaling like 10 to the 2. Now, as I told you, we wanted to really go through all the string axivers, and so we decided to consider also this new type of axionic modes, which was proposed in this work here. And so let me do a brief introduction on this class of axion. So we have to consider, let me consider Calabi-yau, which has a deformed and a resolved side that are connected by a conical transition. So we have the deformed side here that goes into a resolved side. And we know that the change in H11 on the resolved side corresponds on the number of homology generation of the cycles that are shrinking at the conical locus on the deformed side. Now, the authors define the integral of C2 over the 2 sphere, that is a portion of the 3 cycle that is shrinking. Then you can define this thing as in the resolved side as a proper C2 axion that we all know, but this can also be seen in the deformed side as the lowest radii KK mode inside this throat. Therefore, this is a new particle and it's naturally light. Also, in this work, they show that this particle is actually an axion, is an axionic mode because it has a shift symmetry, which is also preserved as a discrete symmetry. So how we give a potential to this new particle? So in this work, the authors propose that this particle receive a potential via this non-perturbative correction to the superpotential, which scales as the warp factor of the throat cubed, where the warp factor is famously the exponent of the ratio of the 2 flux numbers inside the throat. And we will see, we define this as the actually the instanton action of this particle. So now we can proceed. Since we have the instanton action, then we can compute Einstein's F. And as you can see, this is enhanced by the flux number K, and therefore could actually be, again, a good candidate because we want to saturate the weak gravity bound. Now we can compute the mass of this particle, which, as you can see, scales as 6 times the warp factor. However, this is computed only at the no-scale level. And what I did in the other work with Federico Cato, Alessandro Menino, my supervisor, was to introduce Kähler moduli stabilization, so to break the no-scale structure. And actually, the traction mass gets a bit modified because it gets non-trivial mixing with the Kähler moduli stabilization. And therefore, the mass is only suppressed 3 times by the work factor. Okay, so now we have our effective theory for the traction, and one could say, oh, that's really interesting because in principle, this guy can work both for KKLT and LVOS because I haven't specified any regime so far. However, it turns out that for KKLT, we should impose this consistency relation. That means that the work factor cubed should be bigger than W0 square. This is because we don't want the perturbation induced by Gaussian condensation in the bulk to be comparable with the background fluxes at the IR end of the throat. So not to spoil all the stabilization inside the throat at the IR end. And if I plug the values needed for fuzzy dark matter in this relation, then I see that I should ask for at KKLT a value of W0 which should be less than 10 to the minus 15. However, even if this can be engineered in some particular compactification, actually this value in the landscape is highly disfavored. And for this reason, we wanted to keep the discussion as general as possible. And so we say that thraxions are not really possible candidates in a KKLT stabilization. Therefore, we focused only in the large volume scenario, and thraxions in this case can actually be new possible candidates for dark matter, because this is our plot for thraxions. So, okay, we have this huge band because in this case we didn't consider the astrophysical bound, but we just wanted to plot all the parameter space that this particle could have in principle, regardless of astronomical bounds. But however, it turns out that it's possible to, in this regime here of masses, to have a possible candidates. Now let me give.
Sorry to interrupt
yes,
you again.
Yes,
but,
sure.
When you say highly disfavored,
yeah.
How do you measure that?
I
mean, 10 to the minus 50 looks bad, but the log of 10 to the minus 50 doesn't look bad.
Yeah. Yeah,
so
I mean.
Is there a quantitative way to say that it's highly disfavored?
Yes. So I think that a way to say it is that it's like a very fine-tuned case, because you have to engineer your complex structure moduli stabilization in such a way that its value is super low, super small. And this is maybe not the most general case that you can think of. So
good. I was just curious what you'd say. Thanks.
Okay, thanks. Okay, so now let me give you the prescription for my compactification in order to have a fuzzy dark matter particles coming from the thraxions. So as I explained, these are good candidates only in the large volume scenario. However, as opposed to before, these guys prefer a very, very large value for the Calabi-yau volume. And this was shown to be actually statistically disfavored in the landscape because, yes, smaller values for the volume are preferred. And exactly. And also, then one can ask, how general are actually these thraxions? This is another thing that we studied in this paper, starting from this database built by Carta Morris and Westphal. So we have this database of CC-orientifolds, and we have also the CC-orientifold, which can host thraxions. However, we see that when we ask these CC-orientifolds to have a viable effective field theory, then we see that a very small percentage of these orientifolds is able to provide our theory, effective field theory. Actually, it's not a small number, but the total fraction is actually small. It will be very interesting to see what is this number for the Kreuter-Skarker orientifold, but we just have the CC orientifold, so we worked with that. Also, another thing that I would like to say that we studied again in this paper here is how much control do we have on the effective field theory when an axion is present in the game. So, of course, we start with a Calabi-yau manifold. However, when we turn on a potential for the thraxion, if the thraxion doesn't minimize to 0, then we study that the Calabi-yau manifold is broken. And in the end, you're left with just a complex manifold. Therefore, you're losing all the machinery that we know to compute stuff in the 4-dimensional supergravity. And then you can ask, yeah.
About 4 minutes.
Yes, okay. However, as I told you, we are focusing on the easiest setup that we have, and luckily for fuzzy dark matter, all thraxions minimize to 0. So the effective field theory is kind of under control for us, but this is not always the case, and actually general is not the case. Okay, so finally, we can go back to this plot that I showed you before, and now we can understand it better. So all these are all our predictions for the string axions behaving as fuzzy dark matter candidates. And these are all the bands that are right now studied and already studied. So the solid ones are the exclusion bands. So these experiments didn't find anything so far, but the one that you see with only the contour are actually the next generation experiments. And the very, very interesting thing is that our prediction overlaps with all these regions. So if a fuzzy dark matter particle is detected, then this can be the first detection of ultralight axion. And as we show in this work, we have that string theory actually gives perfect candidates for a fuzzy dark matter particles. Moreover, from this work, we can also tell which string axion is the best candidate to fit the parameter space if this particle will actually be detected. And also, we will be able to provide details on the compactification. So, for example, the regime of volumes preferred or the moduli stabilization procedure preferred, and also maybe understand something about the weak gravity conjecture bound and the relation with the phenomenology. So, thank you very much for your attention.
Okay, thank you, Nicole. Are there any questions? I don't see any at the moment, but let me ask one. So how strong are the weak gravity constraints on the scenario? Because there are several ways out. As you know, you could have a misalignment angle that is close to pi that would solve the problem, or you could have another instantons that generate a very negligible potential, something that we call the spectator instantons. So if you factor all this in, some of the theory space that you rule out could be brought back in.
Yes. So I think the hints about the gravity conjecture is to understand whether the right formulation is the strong one or the weak one. So this is the main. So for example, if we find that actually the particle is this one here that is enhanced, but is not the lowest lying instanton that satisfies the weak gravity conjecture, then okay, fine. We have the weak gravity conjecture, but if we find that this particle is actually satisfying also the strong weak gravity, then maybe we can ask ourselves, is the strong gravity really the one that works? For example, this can be an interesting question.
Right. There's a question from Andreas.
Yeah, hi. Thank you for the nice talk. Yeah, it's a very naive question. Maybe you answered it already during your talk and I missed it, but is there a simple reason to understand why the parameter regime for the thraxion is so much larger as compared to the other candidates?
Yeah, so basically this is because we have more freedom, let's say, in our theory. For example, we have flux numbers. And flux numbers, unless you take a proper Calabi-yau and do all the computations, we have a big range of numbers that we can put inside. And this is why we really wanted to plot everything, because if you want here, they can also behave like dark energy, for example, or dark radiation. So this was also like a whole study about the effective theory and the phenomenology of thraxions. And then also they happen to be in the right regime also for fuzzy dark matter.
Okay, and can you also consider something like instanton flux? Would that also increase the limits for the other candidates?
Instanton flux?
Yeah, I mean, you can also have some kind of fluxed instanton sources.
Yeah, I don't know. The other candidates do not depend on flux numbers. All the other candidates, because they don't talk to the compact structure moduli stabilization, so they are separate. And yeah, so does this reply to your question?
Yeah, it does. Thanks.
Okay, thank you.
Okay, Righi.
Hi, I was wondering about multi-axions actually, because of course I think you probably saw this friendship paper recently, and then there's also a bit of work going on about considering the kind of enhancement effects when you have mixings between axions. And so I wonder whether the statement that detecting one of these would be a signature of an axiverse so how do you consider the mixed origins of these axions? Because in principle it's not just a single axion, right?
Yes, exactly. Yes, indeed. So of course here I'm considering only fuzzy dark matter. I don't know, in this friendship of the axiverse, I guess they wanted to do inflation. I don't remember.
I think actually that particular one, they were just looking at QCD axions.
On QCD axions, okay. So we consider models with very low H11, because these are the models in which the weak gravity relation is pushed to the maximum. So if I take more axions, actually S times F becomes lower. So this can be a problem, but I know that this friendship has this enhancement mechanism. So I don't know, this can be interesting to try to in order to have multiple axions to behave as fuzzy dark matter, you mean? So this, for example, this chord structure that they simulate also.
Exactly. So I mean, I think at low H11 you would probably get more masses that were more or less degenerate. And
exactly.
That's exactly exactly the thing that would give this effect.
Yeah. So either they are degenerate, or you have one mass that it's like behaving like the whole dark matter halo, and the other one is staying very low. So if this mechanism is able to give us some kind of like structure, like this can be interesting, I guess.
Yeah. Okay. Thanks.
Thank you. Thank you very much.
Okay, so I think I don't see any more questions. And thank you, Nicole, once again for a very nice talk.
Thank you.